So before we go and do the check your understanding, I want to talk about the quick notes just one more time, and then we're going to do the check your understanding together so that hopefully we can get through this quickly, and we're still playing catch up from having a virtual day and then a 2-hour delay day. So you have to check your conditions if you're going to do the 4 C's for a significance test. You have to check your random, your 10%, and your large counts. For the random condition, you have to quote the text somewhere, and the quoted text shouldn't just say random sample of, and then give me a number. How many people were selected for the random sample? 10% condition, obviously you have to show that. You have to state your population as N, and then large counts, you have to show that as well. Remember, for large counts, you're using P and not P hat. You're not using the sample proportion that was found. You are using the claimed amount for P. And then when we calculate our test statistic, which is Z, we do the statistic minus the parameter, so P hat minus P, divided by the standard deviation. And this is how we calculate standard deviation. Make sure you're using P down here and not P hat. And then the P value is the area that is shaded from P hat to the edge of the tail. It can go on the less than side as well, so it could be on the left or the right, but you go from wherever your P hat is and then more extreme. The P value is the probability of seeing that event happen if the true proportion is really whatever your HO is, whatever your null hypothesis is. All right. You guys ready to try to check your understanding? All right. For most people, cilantro is a delicious spice that can be added to many recipes, but for some, it has a terrible soapy flavor. Scientists believe that about 10% of the population tastes this soapy flavor. Ibis can taste the soapy flavor and believes that it affects more than 10% of teenagers. She takes a random sample of 200 teenagers and finds that 25 of them get the soapy flavor. Do these results provide convincing evidence that more than 10% of teenagers get a soapy flavor for cilantro? State appropriate hypotheses for performing a significance test. Be sure to define the parameter of interest. What would the null hypothesis be here? What is the claim? P equals 10%. Null hypothesis is that P equals 10% or 0.10. What is our alternative hypothesis? Yep, we want convincing evidence that more than 10%. So alternative hypothesis, or HA, is that P is greater than 0.10. What is P? Yep, true proportion of all teenagers who get a soapy flavor for cilantro. Number 2 says, explain why the sample result gives some evidence for the alternative hypothesis. What's the sample result? $25 out of 200. Go ahead and divide that on a calculator for me. What is 25 divided by 200? 0.125, or 12.5%, right? Why does that provide some evidence for HA? Because it's greater than 10% is absolutely correct, which is our claimed value for P. All right, conditions. What's the first condition? Random. Do we get random? Where? Random sample of 200 teenagers. That is exactly what I would want to see there. Random sample of 200 teenagers, quoted right from the text. Why is that important? Yep, so we can generalize the population of all teenagers in this case. What's our next condition? 10%. what would this look like? Absolutely correct. 200 is less than or equal to 10% of all teenagers. Why is this important? So that we can sample without replacement. This is what gives us our independence that allows us to use the standard deviation formula. We have to be able to sample without replacement and that be okay. And then the last condition, large counts. N times P, or 200 times 0.10, we get 20, which is greater than or equal to 10. What is N times 1 minus P? 180, which is greater than or equal to 10, so we are good there. Why do we care about large counts? For normality. We need the sampling distribution of p hat to be approximately normal. So far, so good. Do we understand everything so far? All right. I would like you guys to calculate the standardized test statistic and the p-value in part D. Because we said this is approximately normal, you should also have what for part D? Draw a picture. Draw a normal curve. So calculate Z. Use that with normal CDF to find your p-value and draw a picture of the normal curve. Does anybody have a Z-score? Yep. I got about 1.18. And then to find the p-value, we want the probability that p hat is equal to 0.125, given that p is actually 0.10, so we do normal CDF. My lower bound, because if I look at my picture, it looks like this. My lower bound would be that 0.125. Since we're doing a right-hand tail, my upper bound is something enormous. Mu is 0.10. Standard deviation is about 0.0212. Standard deviation is the denominator of the Z-score. I got about 0.119. If you are getting reasonably close to me on yours, but it's not exactly the same as mine, that is okay. Like if you had 0.118 or 0.12, that would be close enough. Yes?
What's the 0.125 from?
The 0.125 right here? That's the p hat, which came from right here. That came from the sample result of 25 over 200. So now interpreting that p-value, how do we start an interpretation for p? Assuming the HO is true, what's the HO this time? 0.10, p equals 0.10. So assuming the HO is true, p equals 0.10, there is a .119 probability of what happening? Getting a p hat yes. Assuming the HO is true, p equals 0.10. There is a 0.119 probability of getting a p hat value of 0.125 or greater purely by chance. So what conclusion should be reached here? Should a bees reject or fail to reject? Fail to reject. That's like a failure to convict somebody. If you fail to reject, do you have convincing evidence? No. Does that mean that p is actually 0.10? No. It just means that I don't have enough evidence to say that it's not. Just like when somebody goes to court, somebody goes to trial, they might not be innocent. But if they're found not guilty, not enough evidence was brought to say you are not innocent. So the conclusion that we should reach here, as I keep coloring on this, because our p-value, 0.119, is greater than 0.05, we fail to reject the null, and we do not have convincing evidence that more than 10% of teenagers get a soapy flavor for cilantro. I'm going to come around and put a little cup on your desk. Please do not touch the Skittles that are inside. Do not touch the Skittles that are inside it. All right. You guys okay if I switch the screen? Close enough? Okay. Let's go ahead and flip over then to page 7. Can you taste the rainbow? Many students claim that they can taste the different colors of Skittles. Today we're going to conduct an experiment and perform a significance test using the 4 C's to see if this class can really taste the rainbow. So you're going to need a partner for this, and I'm going to partner you guys up so that we can go quickly. You're going to sample 5 Skittles, and you are not going to eat the ones that are in your cup. Nobody has touched the Skittles. I used a Dixie cup to scoop them out and put them in. Only the person eating the Skittles should be the one touching the Skittles, but the person eating the Skittles is not allowed to see the Skittles. So I'm going to partner you guys up. Uwe in London, you two. I'll put you two together. You two. Here. You guys, Javens together. And then Sage and Edgar. Everybody know who their partner is? All right, so here's the way this is going to work. You guys are going to have to take turns. One person will record, the other person will be the taster and the guesser. When it is your turn to be the guesser, you will close your eyes. Your partner will hand you their cup. That's why it's so important that you didn't touch them, because you're going to eat your partner's Skittles. So close your eyes. They will hand you the cup. You're going to reach into the cup. You're going to take a Skittle out and show it to your partner so that they can see what color it is. Then you're going to eat it, and you're going to guess what color it was. Do not open your eyes at any point during these 5 Skittles. Person that is doing the recording, so person that gets to see the M&Ms, do not tell the guesser if they are right or wrong. Simply make a mark on the page if they're right, and don't put a mark on the page if they're wrong. So we're going to figure out exactly how many correct guesses we get out of 5. Every person's going to do 5, so all together we have a class sample that is going to be 90 Skittles. There's 18 people here today. Everybody's going to sample 5, so 90 Skittles total will be sampled. Once the first guesser is done, then you're going to switch positions. The person that was recording will close their eyes. The former guesser will hand them a new cup of Skittles, and they will taste them. If you don't like Skittles, you are absolutely welcome to spit them out. I will get some napkins up here because I know some people absolutely don't like this candy. I'll get some napkins. You can spit it out into the napkin and then throw it away when you're done. There are more than 5 Skittles in every cup. You are welcome to eat the leftovers after you are finished collecting your data. All right? I'm going to give us no more than 5 minutes to collect this data. All right? So let's go. Okay. Number 6. The calculator. And tail. Have you adjust?
I don't know if maybe that is red. Look at my eyes.
Yep, you're going to do 5 each. 5 each.
You see it? See it?
Right. Napkins are up here if anybody needs them.
Wait. Those are. No, you can't change it. I'm not done. Close your eyes. That one right. This is the last one we're gonna go. No, I've got one of them. Okay. The one I'm showing right now. Yes, I see. I'm sorry. Go purple. You say green. Okay, that's all 5, right?
Oh.
Orange? I mean, I didn't. I really thought I would. Do we give the opposite cups?
I mean, whoever had their hand in the cup should be the one that's eating. You're welcome to switch them around if you want to, but whoever had their hand in the cup, that would be. I don't know where their hand is.
And you drive, right?
You got it.
Think we'll be done in about another minute. Yeah, we're gonna tally them all up. So how many total is gonna be 90? 18 people, 5 screens each.
I'm gonna say I'm like perfect. I love it. Oh, me too. Now do M&M's. Right back. We're not gonna work on that. All right. You know, hold on. You know, they're all chocolate. How many days have you recorded this? No, it does. You're doing that. I'll be there. Yes. Okay, so I've met people. I've met people.
All right. How many correct? Out of 90. Hold on. I did talk to everybody in the room, right? With my calculator in my hand. Out of 90, we got 38 correct as a class. So what's our p hat then? How much? 0.42. All right, so we have a p hat of 0.42. We are going to do the 4 C's. Do you guys remember doing the 4 C's with confidence intervals? We do the 4 C's with significance tests also. There's a little bit more that we have to do here because we didn't have hypotheses when we did confidence intervals. We have hypotheses now. We still have to name our procedure. How many samples did we take? This whole class counted as 1 sample. So we took 1 sample, but we're not doing an interval, so it would not be a 1 sample Z interval. We're doing a significance test. So this is a 1 sample Z test for P. Instead of stating a confidence level, we state a significance level. In this case, we're going to use 5%, or alpha equals 0.05. That is a really common one for us to use there. That's that 5% threshold that we've been talking about all semester. What do you think the parameter is? First of all, what letter would I use for the parameter? P, because we're talking about proportions, correct. P equals, what would P equal here? True proportion of correct guesses for all Skittles. What do you think our beginning assumption should be? Do you think we should begin by assuming that students really can taste the different colors or that they can't? Let's assume that they can't. So if you assume that somebody can't actually taste the colors and they're just randomly guessing, how many different colors are there? There's 5 colors. There's yellow, red, orange, purple, and green. 5 colors total. If somebody is just randomly guessing, what % of the time would you expect them to get it right? If somebody's just randomly, let's say I play this, and every time I just say green, 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 green. 1/5, which would be 20%. So if somebody's just randomly guessing, we would assume that 20% of the time they're going to get it right. If they really can taste the rainbow, would we expect P to be higher or lower than 0.20? Higher. So our alternative hypothesis is that P is greater than 0.20. Those are all the pieces that we need for choose. We need to choose the procedure and set it up. So we chose our procedure, one sample z-test for P. To set it up, we need a significance level. We need to know what our parameter is, and we need our hypotheses. After choose, what do we have next? Check. What are the things that we need to check? Random, 10%, and large counts. All right, so random. Did we get random? Yes, this was a random sample of how much? 90. Random sample of 90 Skittles. And why do we care about that? So that we can generalize. Generalize to what? To the larger population. What would be the larger population here? All Skittles, yes. And then we have 10%. So 90 is less than or equal to 0.10 times what? All Skittles, yes, that's our population. Why do we care about that? Yes. So sampling without replacement is okay. And finally, we have our large counts. So we have to do N times P. What is N? 90. What is P? Oh, that's our P hat. 0.20. Remember, we have to use what we're assuming P is, the HO. So 0.20. What is 90 times 0.20? 18. Greater than or equal to 10? Yep, so we're good there. And then we do N times 1 minus P. So 90 times what? 0.80. And we get 72, which is greater than or equal to 10. So we are good. Why is that important? Yes, normality. So the sampling distribution of p hat is approximately normal. All right. So there's our check. Just like when we did confidence intervals, nothing is different about the check at all, except we don't use p hat. We have to use the HO. We have to use what we are assuming p is. General formula for calculate my test statistic is equal to my statistic minus my parameter divided by the standard deviation. What is the test statistic here? There's a letter I'm going to put in instead of writing test statistic. Z. So Z is equal to p hat minus p over the standard deviation, square root of p times 1 minus p all over n. Please make sure to use p, not p hat. Same thing here. Use p. You okay? Okay. Not p hat. So let's go ahead and plug those numbers in. So I have Z equals, here's the only place where I use p hat. What was p hat again? 0.42 minus p, which is 0.20, over the square root of 0.20 times 0.80 over 90. Because I know I need the standard deviation for my picture, I usually do standard deviation separately. 0.2 times 0.8 divided by 90. I got about 0.042 for my standard deviation. And what do we get for our test statistic? You said 5.22? I got 5.24 on mine. Same difference. If you got 5.22, my 5.24, it's close enough. Close enough. What does Z tell me again? How many standard deviations away we are from the mean. And this is saying that we are more than 5 standard deviations away. On which side, left or right? On the right side. How many standard deviations out do we go to get 99.7 of all the area? 3 standard deviations. We're saying we're even further than that. We're 5 standard deviations out. So what would you expect the area under the curve at 5 standard deviations out to be? Very small. We're going to have a very small p-value here. How do I find the p-value? How do I find the probability value? Normal CDF. So normal CDF. I'm going to look to my picture now because this will contain all the information that I need. Right here would be 0.20. So 0.20, 0.042 for my standard deviation. And we were over here with 0.42. So my lower bound would be 0.42. Upper boundary would be something enormous like 1,000,000. Mean of 0.20. Standard deviation of 0.042. Don't forget when you are writing all this out to go back and label what each of these numbers is. This is my lower bound. This is my upper bound, my mean, and my standard deviation. And we end up with a p-value of, I already know it's going to be really small, how many zeros? I'm sorry, I didn't do this on my calculator. E to the negative 8, so 7 zeros, 1, 2, 3, 4, 5, 6, 7, and then what would be the digit? You said 823? 813. So when I get a p-value that is that small, that's not 0, but it's practically 0. So we got a p-value that is incredibly small. If you wrote this as 8.13 times 10 to the negative 8, that would be perfectly fine. You don't have to write out all the leading zeros. But I do need you to know that when we have 10 to the negative power, it's got leading zeros after the decimal point. So we know that we are exceptionally small with our p-value here. Also, don't put e. That e stands for exponent. It's telling you 10 to the power of whatever comes after the e. All right? All right, let's see if we can interpret and conclude. So help me write this interpretation for the p-value. Interpret p-value. How do we start this? Assuming the hoe is true. What was the hoe again? P equals 0.20. Don't forget that P equals 0.20. There is an 8.13 times 10 to the negative 8. Did I write that down correctly? I'm trying to remember it from the previous screen. 8.13 times 10 to the negative 8 probability of getting a p hat of, what was our p hat? 0.42, 0.42, or less, or greater, We shaded to the right, purely by chance. All right, so before we do the conclusion part, here we just interpreted the p-value. I want to make sure that we all understand what this says. So assuming you guys can't actually taste these different colors, assuming that you were just guessing and you're only going to get it right 20% of the time, there is practically a 0% probability that that happens just by chance. If something is practically impossible to happen by chance, there's probably a different explanation for why it happened, right? That's what we said here and what we're going to say in our conclusion. So decision and conclusion in context. Thank you. So because our p-value, 8.13 times 10 to the negative 8, is greater than or less than 5%. Less than 5%, so less than 0.05. We reject or fail to reject? We reject the hoe. And we do or do not have convincing evidence? We do. And we do have convincing evidence. What's our convincing evidence of? Let's see, P was 0.20, right? And that was the assumption that y'all were just guessing. So if we're rejecting the idea that you were just guessing, what do we have evidence for? You can actually taste the rainbow. So we have convincing evidence that the students in this class really can taste the rainbow. Or if I'm going to be a little bit more statsy about it, we have convincing evidence that P is greater than 0.20. Awesome. Real quick, I'm just going to look at the quick notes. We're going to save the check your understanding for later. So looking at our quick notes here, 4C method for inference. Choose, check, calculate, conclude. Choose the procedure, alpha, parameter, statistic, and hypotheses. Check your conditions. Calculate, have your general and specific formulas. You plug in your numbers, draw a picture. Find Z, your test statistic, and your p-value. In the conclude step, you interpret what the p-value means, and you reach a decision with a conclusion. If you do a two-tailed test, if this is one of the ones where we just want to know that it's not equal to the hoe, then we have to take our p-value times 2 because we have a tail on either side. We'll practice what that looks like tomorrow. All right? Yes. Homework is due on Monday. Homework is due on Monday. We will start class tomorrow by doing the check your understanding. And then we will move on to our next activity where we look at not just a significance test for P, but we're going to look at a difference of two proportions.